you'd gone back to the 1980s around here and asked people about the future of semiconductors, most of the, quote, experts on this campus would have told you that silicon was on its way out and gallium arsenide was on its way in because of its higher mobility and you can make faster transistors with it. Well, a major reason for that was that if you also went back to the 1980s, you would discover that almost no one foresaw what was about to happen with personal computers. I know that I was heavily involved with the people at IBM Yorktown at that time, and the hardware people up there thought they were sitting very pretty. Some PCs had started to come out, little desktop devices. In fact, IBM had just introduced a PC, but they were saying that's a rather trivial part of the market. We control the mainframes, and that, of course, is where all the money is. Well, as it so often happens, those of us who foresee the future in engineering are dead wrong. And I can promise you that if you take a survey on this campus of really bright people who are in touch with the pulse of their fields, and you ask them to predict what the breakthroughs will be in the next decade, not 1% of them will get it even vaguely right. And that's just part of the way engineering works. Always has been, always will be. Anyway, the development of the material science of creating these tiny little devices is what's been able to give us powerful computers that sit in these tiny little cases that we have. There are really several steps in manufacture of a device of this sort. The first thing we have to worry about is the chip itself, the single crystal of silicon, which, remember, has to be very high purity and virtually defect-free, because if it was not, we would not be able to control the properties of the silicon by doping. We then use photolithography to locate the regions we're going to dope. We then dope, that is, add the electrically active solutes. We then overlay to create junctions, these metallic junctions between them. We metallize to interconnect those various devices, put down metallic conductors. We then what's called passivating, which is essentially just depositing oxides to insulate and isolate the devices. We'll then take a number of these devices and join them together in higher level packaging to interconnect these various chips. So let's just go through this step by step. We have talked earlier about the Czochralski method and ways in which we could grow large, almost perfect, high purity single crystals. And that's done routinely in plants all over the world right now. Huge pools of electrical quality silicon can be turned out, and that is the template on which we write microelectronic surfaces. The way that we write the microelectronic surfaces is the following. You take your little silicon chip, you coat it with an oxide. Now I need to locate the regions that I'm going to dope with various solutes. The way that I do that is to coat the oxide with a photosensitive coating. And then I do what's called photolithography. I will construct a mask. The mask will have a pattern cut into it, which is just a network of holes, if you want, or slots, that are capable of passing light or some other radiation. I then put the mask over my photosensitive coating, illuminate with light. The light only passes through where the mask allows it to, strikes the coating, and changes it. There are really two kinds of photoresistant coatings. There are photopositive coatings and photonegative coatings. In a photopositive coating, we make changes in the coating that make it more easy to dissolve. In photonegative coatings, we make changes in the coatings that make it less easy to dissolve. So that in one case, we're trying to make this area that the light strikes the place where we will add our dopant. In the other case, we're trying to make this place where the light strikes the area where we're not trying to add our dopant. And what that really has to do with how hard it is to cut a mask that allows you to access the regions that you want to dope with the devices. The minimum feature size that you can put on a surface like this depends on the wavelength of your light. Although these days they are coming up with some new techniques that allow you to focus light to points that are less than the wavelength. So we're actually getting beyond this limit in certain ways. But the feature size is governed by the wavelength of the light. Visible light has a minimum wavelength of about a micron. So if you're going to use visible light for your photolithography, you're stuck with devices that are something like a micron in minimum dimension. Ultraviolet light can go down to a tenth of a micron. Electrons or X-rays can go 0.1 to 1 nanometer. And new and exotic methods, such as methods of using very sophisticated kinds of interference to get visible light to focus to spot sizes less than 1 micron, are constantly being developed. I'll forget the light cutting through directly. Now suppose that we have used photolithography to create a gap. All right, we use photolithography, let me go back a bit. We use photolithography to eliminate the photoresist and to make this area sensitive. Suppose the nature of the photoresist, and this is the most common situation, is such that the region that is struck by the light or the radiation or the electrons is more sensitive to various chemicals that might etch it away. So we etch the photoresist away, and in the same or subsequent process, we etch away the oxide that is directly under the exposed region, and that exposes the surface of the silicon. We etch away the photoresist and etch away the oxide, sometimes in the same step. We can now add electrically active species in many different ways. The traditional way, and the way that you would probably still use today if you took a semiconductor manufacturing lab over in this building, for example, is just to plate what you want to deposit on the surface, let's say phosphorus, and heat this device, this sample up so that you diffuse it into the interior, creating a doped region that looks something like I've shown here. There are a number of ways to do that more precisely. The more precise ways usually involve something like ion implantation, where we take our coated surface, we subject it to bombardment with dopant ions, and we get a dopant distribution something like this. The problem with diffusion as a way of generating your doped regions is that, I think I illustrate this on the next profile, yeah. If I just use diffusion, I get a diffusion profile that looks something like this. The dopant concentration just tails off as you go down into the material, and as you can see, that has the consequence that the conductivity of your semiconductor is going to be a function of distance below the surface. People can cope with that, they've done it for decades, but it is something of a problem. Ion implantation has the advantage that depending on the energy of the ions, you get a distribution that looks something like I've shown here, labeled. The ions coming in with a certain controlled momentum will tend to penetrate a certain specific distance into the material before coming to a rest. So you get a profile that actually peaks out slightly below the surface, something like this, and gives you a profile that is a bit flatter than you would get with diffusion, also a bit more concentrated beneath the surface. So this is an improvement. If you really want a flat profile, you can do something like ion implantation or diffusion, and you can come back and illuminate with, for example, a laser pulse so that you actually melt this region, focus melt this region in which this dopant exists, and in the rapid diffusion in the liquid phase, you can create an almost constant concentration. Which of these techniques you use depend, of course, on how much money you have and how desperately you need to get a really flat profile up here in your device. But there are several of them. Overlay to create junctions. Well, when primary doping is completed, we can recoat, remask, and repattern, and dope a second species to create the desired distribution of junctions. For example, suppose the first thing we put down was P, like boron. We can then come back, recoat, redeposit, and deposit phosphorus to create N-type regions to create an NPN bipolar junction that you see here. Or alternatively, we can come in, recoat, re-etch, and put the doped material here on the surface to create a device that looks something like that. In many semiconducting devices based on silicon, engineers are able to cheat. And the reason is that silicon naturally contains, or a lot of silicon as it's manufactured, naturally contains a distribution of boron. Very difficult to get that boron out, in fact, because of its resistance to things like zone melting. So you begin with a silicon that's basically p-type. So one of the things you can do is just live with that. Come in, use phosphorus to implant n-type regions, and you have a natural NPN junction. So you can do that, or alternatively, if you really want to control them, you can dope one species and then the other to create a controlled device of the surface. Metallization. The metallization process is actually, when you hear someone talk about the dimension of a device, we're going to 10th micron technology or 100 nanometer technology, which is kind of the standard in the industry of how far they've gone in miniaturization. People sort of think that refers to the devices. It really doesn't. That refers to the dimension of the metallization you use, which turns out to be the connection between the devices, and is the thing that you really have to get very fine if you're going to miniaturize. And that became a serious problem, gosh, through the late 80s and early 90s in particular. In those days, almost all devices, and still the less expensive devices, use aluminum as the connector. Aluminum is relatively easy because aluminum can be easily etched in the manufacturing process. And what you can do in that case is, for example, you can put down an oxide, put cuts in the oxide where you want the metal to contact the device, deposit the metal, and then if it is aluminum, you can etch it away in the regions that you don't want it to be using another mask, and in that way create a nice pattern of aluminum that can be very fine. The aluminum had two problems. One problem was that aluminum is not as good a conductor as, for example, copper or gold, and copper would be relatively inexpensive. And the better your conductor, the faster you can make your device operate, or the more you can miniaturize it for a given performance criterion. So that was a disadvantage of aluminum. Another disadvantage to aluminum was that it was liable to electromigration. Now, I don't have time to go through that in great detail, but essentially what's happening is you start pushing current through these devices. Even though the current is very small, when the devices become very small in cross-section, the current densities become very high. When current is going through a device like aluminum, it has a tendency to push the atoms along with it. So you have atoms moving with the current, vacancies going in the other direction, and you can develop vacancy agglomerations which lead to actual failure of the devices. And electromigration failure was a serious reliability problem, or as recently as 25 years ago or so. To avoid that, you wanted to go to copper, better conductivity and also more resistant to electromigration. The problem with copper was there was no good way to pattern it and then etch it. So people were constantly looking for a way to use copper in these very, very fine interconnection lines between devices. Ironically, I was at that time consulting with two different companies working on microelectronic packaging. They were both going after copper. They were both coming up with exactly the same solution at exactly the same pace, with no conversations with one another. And it was kind of fascinating to see these guys telling me that they just invented a new technique. It was precisely what the other guy just invented the week before. And what people came up with, they weren't the only ones, kind of the whole world discovered a technique which goes back to the making of, well, particularly the art of lacquer boxes in China a couple of thousand years ago. If you've looked at these, lacquer jewelry boxes in particular, a lot of them have very complicated line interlays, and they're made by something called the Damascene process. Now, Damascene comes from Damascus. You'll find all kinds of things named after Damascus. You hear about Damascus swords, the Damascene process for lacquer boxes, and all these things. You get the impression that Damascus was the center of technology for 1,000 years. It actually wasn't. What Damascus was the end of the caravan route that came out of Asia. So everything that was discovered in Asia, brought to Damascus, and then sold in Europe, turned out to be called Damascene something or another, Damascus steel. Anyway, what the Damascene process is, and it's still used today, you lay down the lacquer. Then you take the pattern you want, and you come in with just a tool of some sort, and you dig a furrow, narrow furrow, that is the pattern that you want to put on the lacquer box. Then you plate it with gold. Then you just come in with an abrasive, and you just polish away the gold on the surface. Well, where the gold is into the groove that you cut, it doesn't polish, so it stays there. And that is, I don't think I have a good picture of that here, do I? No, I don't. That's essentially what the Damascene process for using copper interconnects is all about. You come in, you cut the places you want the copper to be in some oxide layer, you then plate copper everywhere, you then come back and polish the surface. And when you do that, you remove the copper everywhere but within the grooves where you want it to be. And in that way, you can create this very fine copper pattern by the Damascene process. So these days, the fancy electronics, miniaturized, it uses copper. Some of the simpler, cheaper stuff still uses aluminum because it's cheaper and easier to use, and if you don't need the higher conductivity or electromigration resistance of copper, you just don't do it. Passivation. After you have put down your interconnects and your devices, the next thing you have to do is passivate, cover it again with oxide, and seal your whole unit. Any microelectronic device is a corrodant's paradise. You have dissimilar metals, dissimilar materials in contact with one another intimately everywhere. They're conducting electricity. They will dissolve in any corrodant there is. So it is critically important that you hermetically seal any microelectronic device after making it. You do that really in two stages. You put oxide over the devices and the interconnects that connect them, and then because you've got to have wires coming in and out, you generally have hermetic sealing with polymers of some kind around the entire device, and all that's coming in and out of the wires. Believe me, if these fellows could find a way to get the current in without using wires, they would do that. Because anything you have that is a conduit into your material seriously risks failure by catastrophic corrosion. So hermetic sealing is a very big issue with microelectronics. Well, then, of course, finally, you interconnect the devices. You solder chips on the boards. You solder the boards to one another to make the electronic device, and then your device is finished. This area, electronic packaging, microelectronic packaging, which kind of covers everything from putting down the metallization to hermetic sealing to putting the wire interconnects and so on, the solder contacts, has become a large and increasing part of microelectronics. And for a very simple reason. I can recall, gosh, it was about 20 years ago, we had the then Vice President of Technology from IBM come in and give a talk about where he saw the future and the need for people. And he put up a simple chart. He says, if we take a microelectronic device, typically the sort then manufactured by IBM, the total time, you talk about the cycle time, how many operations you can perform per unit time. Of the time required to perform an operation in those days, roughly 20% of it was the time for the operation in the device, and 80% of it was the time you needed for the current to run back and forth through the package and communicate from device to device. Then he put another chart. He said, here are the number of engineers in the United States who are working on the devices, huge number. Here are the number of engineers who are working on packaging, small number. And he said, where do you think you ought to go to work? And sure enough, the employment in the packaging area has kind of boomed since then. It's become a critically important area of microelectronics. So if you go to a place like Intel these days, you'll find probably many more people working on interconnecting devices and how to configure them and so on than you'll find working on the devices themselves. So because that's where you can save time, and time is a big deal in microelectronics. Yeah.
When you're talking about innovation, why
Oh, they do that. I should have mentioned that. There are many times that you will do things like overdoping silicon to get a local connector. There are other things you can do too. The problem that you have with those is that they're really lousy metals. So the only time you're going to take that approach is when you're connecting two devices that are right next to each other. So it's actually faster to send it through a high resistivity silicon than it would be to send it up to a copper line and over to the next one. But yeah, that is used. Those techniques are used. They're just less common and less critical than these other forms of metallization. Yes, it's if you take your computer apart and start looking at the clips, you'll see probably copper, unless they save money on your computer, in which case it'll be aluminum. So the high performance things are all copper. I really don't know how much aluminum is still used today, but as of a few years ago, quite a bit of it still was, because it's cheaper and easier to use. And if your computer will work fine with aluminum, why pay for copper? Why not save yourself a couple $100 on the computer? You only want to pay for things that you will actually see in terms of increased performance. And those kinds of decisions are always made in engineering. Well, that finishes what I want to say about semiconductors. We now turn to two subjects that kind of get tied in together: insulators, dielectrics, and photonic materials or optical materials. Now, back when I first started teaching this course, in fact, for the first 15 years or so I taught it at least, this was a part of the course that I had real difficulty getting excited about. Now, who cares about insulators? Optical materials, God, that's Windows. I don't care about those either. They kind of had to be covered for their importance in material science, but they were, from an engineering point of view, apparently rather dull subjects. God, how the world has turned. In microelectronics, many of the most exciting jobs and the most exciting problems are now associated with dielectrics. And of course, you all know about the photonic revolution, which is a change that almost all the way that information is exchanged, and many, many things are done. So there's been a dramatic revolution in the last couple of decades, a few decades actually now, that has really changed the relative importance of insulators and photonic materials in material science. So let's talk first about insulators. Insulators are also called dielectrics. In the solid-state physics book, I don't think you'll find the word insulator. They're all called dielectrics. The difference between solid-state physicists recognize two kinds of materials: dielectrics and metals. The two kinds of materials are whether they can support an electric field. If you have a conductor, you put on an electric field, the charges will move so the electric field goes away. The equilibrium electric field inside any conductor, even a semiconductor, is zero, because current will continue until the electric field is removed. Insulators or dielectrics are materials that ideally don't conduct at all, so they can support an electric field. So when we want to support electric fields, we use dielectrics. When we don't want to support electric fields, we want to conduct electricity, we use conductors. A dielectric is basically a material that has a large band gap. If we get the band gap above about 2 electron volts, the thermal conductivity is very, very low, and for most purposes you can ignore it, particularly at room temperature and such times. So anything with a band gap above about 2 electron volts is an insulator. Most good insulators up to 3 electron volts or higher have very low conductivity. There are basically two engineering uses for insulators. One is to separate conductors. You do that all the time. You have a wire running through the house that has a piece of polymer on it so that when you touch the wire you don't get shocked. It's a very good idea. So it's separating conductors, the wire in your finger. When you separate conductors, you really are trying to do two things. You don't want any current to leak through the insulator because you don't want the conductors to interfere with one another. You also don't want any indirect interference. A moving charge can induce charges in any nearby conductor. So you have to worry about conductors talking to each other. Now, that isn't much of a problem in your electric train set at home, but it's a huge problem in things like microelectronic devices, where you are passing information through wires. And if these wires start talking to each other through induced charges, then this information is going to go leaking and distorting, and many bad things are going to happen. So it's a huge issue in microelectronics to get the kind of insulators that not only will prevent the conductors from conducting to one another, but will also prevent them from talking to one another, because they will whisper secrets that they're not supposed to know about and they'll mess things up. So that's one thing, separate conductors. The other thing is to support electric fields. Two obvious places we support electric fields is the storage of energy and things like capacitors. You go by any PG&E yard, you see the great big whopping capacitors out there which are storing energy. You also use electric fields, for example, to induce charges in field effect transistors. And there are many, many other applications of electrical engineering where you want to support electric fields and utilize those electric fields. These are a couple of examples. Material properties, there are 3 material properties we ordinarily talk about with insulators. The first is the critical field, ability to insulate. No insulator is perfect. If we build the field across an insulator to a big enough value, it will discharge. It will conduct electricity. The thing that you rarely see out here, but if you grew up in the southeast like I did, you see on an almost daily basis are bolts of lightning coming from the sky. Classic case of an insulator whose critical field has been exceeded between the clouds and the earth, and the result is a bolt of lightning. When I first came out to Berkeley way back when, I turned on the 5 o'clock news, and an item on the 5 o'clock news was that a bolt of lightning had struck a tree in Palo Alto. And I'm sitting here thinking, are these people crazy? In most of the world, that's a daily occurrence. Anyway, the second property of internal field, supporting internal fields, is the dielectric constant. We would like the engineering drive is for the extremes in dielectric constant. High dielectric constants mean high induced charge. So capacitors want high dielectric constants. Field effect transistors, you want materials with high dielectric constants. And particularly in connection with MOSFETs, there's a constant drive in the electronics industry to produce better and better insulators with higher and higher dielectric constants. We'll talk about the material science of that in just a moment. At the same time, in the microelectronics industry, there's a huge drive to get things with very low dielectric constants, because it turns out that the dielectric constant governs the crosstalk between electrical conductors, how much they interfere with one another. So if you want two conductors to be very close together but not talk to one another,